You're witnessing the dawn of a new era in astronomy. This image, the first light from the world's most powerful digital eye, represents not just a photograph, but a fundamental transformation in how humanity observes the universe. The Mega 3200 megapixel camera, now operational at the Vera C Rubin Observatory, perched 2,715 meters above sea level in Chile's Cerro Pachon, has just captured what no instrument before it could achieve: a view of the cosmos so vast, so detailed, and so data-rich that it requires an entirely new vocabulary to describe it. The target of this inaugural observation is the southern expanse of the Virgo cluster, a gravitationally bound collection of over 1,300 galaxies located 54.8 million light-years from Earth. When we say cluster, we're describing something almost incomprehensibly vast, a structure spanning 15 million light-years across, containing more mass than a quadrillion suns. The photons that created this image left their sources when Earth's climate was 14 degrees Celsius warmer, when the Himalayas were still rising, and when our earliest primate ancestors were just beginning to evolve. Yet this camera captured their entire journey's end in mere nights of observation. Look closely at this cosmic tapestry, and you'll see the universe revealing itself in layers of complexity that previous telescopes could only hint at. In the foreground, stars from our own galaxy blaze in a spectrum of colors. Blue supergiants burning at 30,000 Kelvin, white dwarfs compressing matter to densities of tons per teaspoon, and red giants swollen to hundreds of times our sun's diameter. Moving deeper, spiral galaxies unfurl their arms in magnificent detail, each one containing 400 billion stars, their blue-white star-forming regions contrasting against older, yellower stellar populations in their cores. Further still, elliptical galaxies appear as golden orbs, their stars so old that blue light has long since faded, leaving only the warm glow of ancient suns. And in the deepest background, red-shifted galaxy groups appear as rust-colored smudges, entire clusters racing away from us at significant fractions of light speed. The numbers attached to this single observation challenge our ability to process information. This mosaic, assembled from 1,189 individual 30-second exposures taken over just 7 nights, contains visual data on more than 10 million galaxies. Let that sink in. 10 million separate galaxies, each containing hundreds of billions of stars, each star potentially hosting planetary systems. If you spent just 1 second looking at each galaxy in this image, it would take you 115 days of continuous observation. No sleep, no breaks, to see them all. Previous survey telescopes would have required years, possibly decades, to capture equivalent data. The Sloan Digital Sky Survey, revolutionary in its time, took 8 years to map a similar number of objects. Rubin did it in a week. No instrument in history, not the Hubble Space Telescope with its exquisite resolution, not the James Webb with its infrared prowess, not the massive ground-based Keck Observatory with its 10-meter mirrors, can match what this camera just accomplished. It's not about taking the sharpest image or seeing the furthest object. It's about capturing the universe in both breadth and depth simultaneously. Imagine having eyes that could read a newspaper and see the entire horizon at the same time, then being able to do it again 3 nights later to spot every change. That's the revolutionary capability we're witnessing. But this stunning first light image? It's merely the overture to a symphony that will play for the next decade. Starting in 2025, the Vera C Rubin Observatory will embark on the most ambitious astronomical survey ever attempted, the Legacy Survey of Space and Time, LSST. This isn't a mission to observe specific targets or pursue particular phenomena. It's a systematic, relentless documentation of everything. Every star, every galaxy, every moving object, every transient flash, visible from the southern hemisphere. The observatory will photograph the entire southern sky 825 times over 10 years, creating not a map, but a movie of half the universe. The engine of this revolution is the LSST camera itself, a 3200 megapixel colossus that redefines what we mean by digital imaging. To call it a camera almost seems inadequate. It's more accurate to describe it as a photon-harvesting supercomputer with optics attached. Every component pushes the boundaries of what's physically possible. Sensors cooled to 100 Dalils to eliminate electronic noise, shutters that can open and close in under a second, despite being 2 meters across, filters that can switch automatically to observe in 6 different wavelengths. The entire assembly weighs as much as 3 cars, yet maintains optical alignment to nanometer precision, steadier than atoms vibrate at room temperature. When this camera operates at full capacity, it will generate 20 terabytes of data every single night. That's equivalent to the entire printed collection of the Library of Congress, created fresh each evening. Over its 10-year mission, the LSST will produce 60 petabytes of raw data, enough to fill 12 million DVDs. If you started watching this data as a movie at 30 frames per second, it would take you 1,000 years to view it all. Processing this information river requires 100 times more computing power than previous astronomical surveys, with algorithms that can identify, classify, and flag interesting phenomena in real time. Within 60 seconds of capturing an image, the system must compare it against previous observations, identify changes, and alert astronomers worldwide to anything unusual. How does this observatory accomplish what every telescope before it could not? How does it see everything, everywhere, all at once? The answer lies not in a single breakthrough, but in the convergence of multiple revolutions. Detector technology pushed to theoretical limits, optical designs that seemed impossible a generation ago, and computational capabilities that didn't exist when this project was conceived. Understanding this convergence is understanding the future of how we study the universe. For 4 centuries, since Galileo first pointed a telescope skyward in 1609, astronomy has been the science of patient observation and careful documentation. Astronomers would spend entire nights capturing single images, sometimes exposing photographic plates for hours to gather enough light from dim objects. These observations gave us catalogs of stars, maps of galaxies, and classifications of celestial phenomena. We learned what was out there, where it was located, and how it was structured. But we were essentially taking still photographs of a universe in constant motion. It's like trying to understand ocean waves by looking at postcards. You see the water, but you miss the dynamics. The cosmos is far more active than our static images suggested. Stars explode without warning, brightening a billion-fold in days. Asteroids tumble through space, their trajectories constantly altered by gravitational encounters. Black holes devour matter in violent feeding frenzies that flare across the electromagnetic spectrum. Galaxies collide over millions of years, their shapes morphing like cosmic kaleidoscopes. Dark matter's invisible hand guides the architecture of the universe through gravitational effects we can only detect by watching how things move over time. Traditional telescopes, optimized for deep, narrow observations, miss most of this action. By the time they return to re-observe an area, the interesting event has often passed. The Vera C. Rubin Observatory represents astronomy's transition from photography to cinematography. Instead of capturing isolated moments, it records continuous change. This isn't just a quantitative improvement, seeing more things faster, but a qualitative transformation in how we understand cosmic processes. It's the difference between having a dictionary of celestial objects and understanding the grammar of how the universe constructs itself. When you can watch the universe evolve in near real time, patterns emerge that were invisible in static observations. Cause and effect become traceable. Rare events become detectable. The universe transforms from a collection of objects into a dynamic system. Think of the Rubin Observatory as humanity's cosmic security camera, but one with extraordinary capabilities. Imagine a surveillance system that could monitor every person on Earth simultaneously, track every car, notice every light turning on or off, and remember where everything was for the past decade. Now scale that up to cosmic proportions. Rubin watches billions of galaxies, tracks millions of asteroids, catches thousands of supernovae, and remembers the position and brightness of every object it has ever seen. It's not just recording, it's actively comparing, constantly asking, what changed, what moved, what's new, what disappeared. The LSST camera is an engineering masterpiece that required solving problems that didn't have solutions when the project began. The heart of the system is a focal plane consisting of 189 charge-coupled device (CCD) sensors, each one a 16-megapixel array capable of detecting single photons. These aren't ordinary CCDs like those in consumer cameras. They're scientific-grade sensors with quantum efficiencies exceeding 90% in some wavelengths, meaning they capture nearly every photon that hits them. The entire focal plane spans 64 centimeters across, about the width of a large pizza, making it the largest digital sensor array ever constructed. To put this in perspective, the human eye's retina is about 20 millimeters across. The LSST's retina is 30 times larger. With 1,600 times more pixels than the human eye has photoreceptors. The camera's 3.2 gigapixels means each full-sky image contains 200,000 individual measurements of light. If each pixel were a person, you could give everyone in India, China, and the United States their own pixel, and still have pixels left over. Displaying one image at full resolution would require a grid of 1,500 high-definition televisions, enough to cover a football field. Yet this massive sensor must be kept at 100 degrees C, colder than the coldest temperature ever recorded in Antarctica, to prevent thermal electrons from creating false signals. The cooling system must maintain this temperature while the telescope slews across the sky, fighting against Chilean desert heat that can exceed 30 degrees Celsius during the day. What makes Rubin truly revolutionary is its field of view, 3.5 degrees across, or about 40 times the area of the full moon. Most large telescopes see a patch of sky smaller than the moon. Hubble's field of view would fit 150 times inside Rubin's single frame. This wide field comes from a three-mirror design that required breaking the rules of traditional telescope engineering. The primary mirror, 8.4 meters across, had to be ground to a shape that varies from a perfect parabola by amounts measured in nanometers. The secondary mirror, 3.4 meters across, is the largest convex mirror ever made. Together with a third mirror, they create an optical system that delivers sharp images across the entire huge field, something physicists thought impossible until sophisticated computer modeling proved otherwise. Here's how Rubin transforms photons into scientific discovery. Every 39 seconds, the telescope captures a pair of 15-second exposures of a specific patch of sky. The dual exposure helps identify cosmic rays and satellite trails that might contaminate single images. The telescope then slews to an adjacent field, a movement that takes just 5 seconds despite moving a 350-ton instrument, and repeats the process. Over the course of a night, it captures roughly 1,000 image pairs, systematically tiling the sky like a photographer creating a panoramic mosaic. But unlike a regular mosaic, where images are simply stitched together, each Rubin image is immediately compared against every previous image of the same region. The key innovation is something called difference imaging, a technique that sounds simple but requires enormous computational sophistication. For every patch of sky, the observatory maintains a template, a deep, high-quality reference image created by combining hundreds of previous observations. When a new image arrives, the system performs precise astrometric and photometric calibration, accounting for atmospheric distortion, telescope flexure, and a dozen other variables. It then subtracts the template from the new image, pixel by pixel. What remains is pure change. New supernovae appearing as bright dots, asteroids revealed as moving streaks, variable stars showing altered brightness. It's like having a spot the difference puzzle, where the universe itself is changing between the two pictures. Within 60 seconds of detecting a change, Rubin's automated systems spring into action. Machine learning algorithms classify the detection. Is it a known asteroid on a predictable path? A variable star following its expected pattern? Or something entirely new? For interesting events, supernovae, potentially hazardous asteroids, unusual transients, the system broadcasts alerts to observatories worldwide. These alerts, expected to number 10 million per night, enable follow-up observations with specialized telescopes. It's a cosmic early warning system that turns the entire global astronomical community into a coordinated response team.